Thank you for coming, and thanks to the organizer. I will talk about Morse boundaries for finite generated groups. So in geometry group theory, to study a group, we consider a space where the group acts nicely. So the boundary of the space is helpful to understand the given group. So today I will see some boundaries and how they are used for our groups. So here is the outline. First of all, we briefly review hyperbolic spaces and hyperbolic groups, and then define group boundaries of them. And we will define contracting boundaries of Capsular space. And finally, we see Morse boundaries of proper metric spaces. So yeah, let's briefly review hyperbolic space. A geometric metric space is called delta hyperbolic if for any geodesic triangle is delta thin. So we have this picture in our mind. So like we have very thin triangle, X, Y, Z. So this side is contained in delta neighborhood of two other sides. So we have this picture in our mind. And how can we define hyperbolic group? Well, we can consider a natural proper metric space where the group acts nicely, which is Kelly graph. So the Kelly graph is a graph whose vertices are group elements, and there is an edge between two vertices if they differ by a generator. So a group, finite generated group, is called word hyperbolic if there is a finite generating set S, such that the Kelly graph is delta hyperbolic. Now here is an example. The example is about an infinite cyclic group. So first of all, I will pick my generating set S consisting of A and A inverse. Then as we saw, the Kelly graph is an infinite path. So this is zero hyperbolic space. So we know G is a hyperbolic group. And now I will take different generating set S prime, which consists of A squared, A cubed, and their inverses. Then 2 and 3 are relatively prime, so it is a generating set. And the Kelly graph looks like this. So I think you guys all already know this. Like here is an edge because they differ by A cubed, something like that. So the Kelly graph is dependent on the generating set, but there is a relation. Two metrics are very similar by some scaling. So in particular, in this case, we have these inequalities. So the distance between 2 points in this graph has bounds with respect to the distance between 2 points in this graph. So we need the notion of quasi-isometry. Yeah, this is a review, but a function between two metric spaces is called a quasi-isometry if there is a K and C, which satisfy two conditions. So the first one, for any point in codomain, there exists a point in domain such that the distance between Y and the image of X is less than or equal to C. And the second condition is for any 2 points on the domain, we have the following inequalities. We saw this one a lot of times. And as the previous example, between two Kelly graphs, there is a quasi-isometry. And hyperbolicity is a quasi-isometry invariant, which means if X is hyperbolic, and there exists a quasi-isometry function f between x and y, then y is a hyperbolic. So if a Kelly graph is hyperbolic, then the other Kelly graph is also hyperbolic. Now let's define group boundaries of hyperbolic spaces. So let X be a proper hyperbolic metric space. Then for the fixed point P, the group boundary is equivalent classes of geodesic rays with the base point P. So here two rays are equivalent if their Hausdorff distance is bounded by uniformly bounded by a constant k. So Hausdorff distance means gamma 1 is contained in the k neighborhood of gamma 2, and gamma 2 is contained in k neighborhood of gamma 1. So as I said, the Gromov boundary is defined by this, and it has the following topology. So for any point x on the boundary and non-negative constant r, we can define Vxr. So a point on the boundary y is in this set if for some geodesic rays gamma 1 and gamma 2 starting at the base point P, and gamma 1 represents x and gamma 2 represents y, and the limit of inf of the Gromov product of gamma 1 and gamma 2 is bigger or equal to r. Here, this notation, the Gromov product, means this one. So let's think about it in a triangle. So we are in the hyperbolic space. So my triangle is very thin. So with vertex x, y, z, then I can divide the triangle into 6 sides. So like say here is my A, and the same length is A here, and here say B, then the same length B here, and this side is the same as this. Then think about this notation. Then this side plus this side minus this side, and divide by 2. So actually this one is the Gromov product of x and y with respect to z. So indeed this part. So now we have 2 rays with the base point P. So I have 2 rays, gamma 1 and gamma 2. So indeed I will think about some point here, and I consider this triangle. So the Gromov product is here, gamma 1t, gamma 2t, p. So actually this gamma 1 and gamma 2 travel close for approximate r distance, because like here they they travel very close. So here is like they travel close for approximate distance r. So this is the topology, and these sets form a basis for the topology of the Gromov boundary. Now see some examples. So the first example is let x be a real line. So x is a real line. Then pick a base point, P. Then we have just 2 geodesic rays, like this side and this side. So the Gromov boundary is just 2 points with discrete topology. And the second example, let x be a metric space like this. And I will pick my base point P there. Then I will think about 2 geodesic rays. The first one is this horizontal line, and the second geodesic ray is this line. Then 2 geodesic rays travel close forever. So they go to the same point, same leaving point. And think about the other geodesic ray, this one, or that one. Then also they also travel close to this geodesic ray. So in this side, they go to the same point, same limit point. And the same story for the other side. So the Gromov boundary is indeed 2 points with discrete topology. And the third example, let X be a hyperbolic space with dimension n. Then the Gromov boundary is Sn minus 1. So think about n is 2. And if you are familiar with the disk model, and pick your base point, then from here to any point on the boundary, there is unique geodesic ray. So the boundary of H2 is just this circle. And here is very important theorem. Kim also mentioned this theorem. So let X and Y be proper hyperbolic metric spaces. Then a quasi-isometry between two spaces induces a homomorphism between two Gromov boundaries. This is because a geodesic ray in hyperbolic metric spaces has very good property. So more precisely, let gamma be a geodesic ray in X. Then first of all, gamma is delta slim, which means there exists delta such that for any point X and Y on the ray, the distance between the projection of X and any geodesic with endpoints X and Y is less than delta. So the picture. So delta slim. So I have gamma. This is geodesic ray. And for any point X and any point Y here, and think about the projection, then any geodesic with endpoints X and Y, this distance is less than delta. And the second property, gamma is decontracting, which means there exists D such that for any 2 points in X, if the distance between X and Y is less than the distance between X and its projection on the ray, then the distance between two projections is less than D. So the picture is I have geodesic ray gamma, and if the distance between X and Y is less than the distance from here to here, then the distance between two projections here is less than D. And lastly, gamma is n Morse. So yeah, also it is mentioned Olga's talk and Kim's talk. There exists a function n such that for any KC quasi-geodesic beta with endpoints on gamma, then beta is in nkc neighborhood of gamma. Here, quasi-geodesic means it is similar to geodesic, but there is multiplicative error k and additive error c. And here, nkc means the value of the function when the domain is k, c. So, lastly, n Morse. So I have gamma, a geodesic ray, and any quasi-geodesic with endpoints on gamma like this. Then actually beta, like this, say KC quasi-geodesic. Then beta actually contains in n the neighborhood of nkc of gamma. Now define Gromov boundaries for hyperbolic groups. Let G be a ordered hyperbolic groups. Then the Gromov boundary is defined by the Gromov boundary of the Cayley graph. It is well defined because we know there exists a quasi-geodesic between two calligraphs, and the group boundary is quasi-isometric invariant, so it is well defined. And we saw this lemma several times, Sparkle-Miller lemma. From that, G is hyperbolic if and only if G admits isometric, properly discontinuous, and co-compact action on a proper hyperbolic metric space is X. Moreover, the group boundary is quasi-isometric invariant. So in this case, the group boundary of G is homeomorphic to the group boundary of X. So see some examples. So let G be a free group with n generator. Then actually we can find the calligraph easily in this case. So the calligraph is the space of regular 2n valent tree. So the group boundary is a counter set. Now the second example, G be of the fundamental group of S of G, where S of G is a closed oriented surface of genus G. Then H2 is the universal cover of SG. Then the fundamental group acts on the universal cover properly and co-compactly. So instead of finding the calligraph using the space, we know that the group boundary of G is homeomorphic to the group boundary of H2, which is S1. Now see some results and an application. So let X be a proper hyperbolic metric space. Then the union of X and the group boundary is compact and metrizable. So as a topological space, it is a very nice space. And as I said several times, the group boundary is a quasi-isometric invariant, very important one. And for any 2 points on the boundary, there exists a geodesic ray with the endpoints are X and Y. And here is a dynamical result. So let G be a word hyperbolic group, and let G be an element of infinite order. So it has 2 limit points, G plus infinite and G minus infinite. Then for any open set U and V on the boundary with G plus infinite is in U and G minus infinite is in V, then there exists n such that if G to the n acts on the complement of V, then it contains in U. So visualize the theorem. So say this is my boundary, the group boundary. Then I have an element of infinite order. So here I have 2 limit points, G plus infinite and G minus infinite. Then for any open set U and V, like this, so the theorem says that there exists n if G to the n acts on the complement of V, then it goes to this set. And we can do the same thing for the inverse as well. So I have the same picture. So I have U and V, the open set. Then for inverse, I also say there exists n prime such that if G to the n prime acts on the complement of U, then it goes to V minus n prime. So that's why we call this theorem north-south dynamics, because this pole and this pole act like north and south. So to get some information about the group, we need one more lemma, which is Pimple Lemma. We did it by more general statement. Let G be a group with a group action on a set X, and let A and B two non-empty subset of X such that neither is contained in the other. Then suppose two subgroups H and K satisfy two conditions. So the first condition is for any non-trivial element in K, if G acts on A, then it is contained in B. And for non-trivial element in H, if H acts on B, then it contains A. Then the conclusion is the subgroup generated by H and K is a free product of H and K. So we have two lemmas. Now use that information for our group. Let G be a word hyperbolic group, and now suppose that G has two infinite order elements G and H, and their limit points are distinct. So now I have two limit points. H and G. Here H plus infinite and H minus infinite. And take open sets A plus, A minus, B plus, and P minus. So I say here is my A plus, and here is my A minus, and here is my B plus, and here is my B minus. Then first of all, I will use north-south dynamics. I'll say the union of A plus and A minus is A, and B is the union of B plus and B minus. Then by north-south dynamics, there exists M and N such that G to the plus minus M acts on B, then it contains A, and H to the M plus minus N acts on A, then it contains B. Because B contains in the complement of A, so like there exists some G to the M, because this contains in the complement of A. And like we can take the maximum, so there exists the same M, like it goes to this set. So we can do the same thing for A set, so we can find M as well. Then in particular, we have this guy, because this is true for Then now we can use Pimple Lemma, because we found appropriate sets. Then we know the subgroup generated by G to the M and M to the M is a free product of two cyclic subgroups. So here we know that every non-element hyperbolic group, meaning it has two infinite order elements, then contains a free subgroup of length 2. So from the group boundary, we know some structure of hyperbolic group. Furthermore, like there are a lot of applications for group boundary. Now let's move on contracting boundaries of cat-zero spaces. Now we are in cat-zero world. So let X be a proper cat-zero space. Then unfortunately, the group boundary is not a quasi-isometry invariant, because they behave very badly. So In 2013, Charney and Sultan introduced a new boundary for cat-zero space, so which is called the contracting boundary. So the contracting boundary is the subset of the Gromov boundary as a set, consisting of just contracting geodesic rays, meaning like just collect geodesic rays which have this property. And they gave the following topology. So as I said, the contracting boundary is the union of these sets depending on D. And each set has the subspace topology of the Gromov boundary. And then take the direct limit for the contracting boundary, which means an open set, a set is open in the contracting boundary if and only if the set is open in each subspace topology. So let's see some examples. So first, say my space is a Euclidean space with dimension n. Then it is flat, so there is no contracting geodesic rays. So the contracting boundary is empty set. So say n is 2. And check this property. So R2. And think about any geodesic ray in R2. And think about the projection of the ball. Then the projection of the ball is just the diameter of the ball. So this is just this. So if my center goes away and my ball is getting bigger, then there is no like uniformly bounds for the projection. So there is no contracting geodesic rays. And let the second example, let X be a delta hyperbolic space. Then, as I said, every geodesic ray is decontracting for some D. So the contracting boundary is indeed just this set. And it has the subspace topology. So it is homeomorphic to the Gromov boundary. So it is a generalization. And lastly, our space is R2 free product and R. So now we know this is cat-zero from Kim's lecture. And like we know like R2 there is no contracting geodesic rays, but R is hyperbolic space. So then what is the contracting boundary of X? So X is R2 cross R. This is free product. So the picture is like I have plane, and each point I have R. I will draw some of them. R, like for every point. And for every point in R, I have plate. I have R2 as well. Like this, something like that. So say my base point is here. And think about some geodesic rays. Then if my geodesic ray just travel in R2, like forever in R2, then it cannot be a contracting ray because in R2 we cannot, we don't have any contracting ray. So it should be moved like this. Like here is another plane. Like it should be like this to be a contracting ray. So the contracting ray, so the contracting boundary is consisting of a geodesic ray with the length of segments of gamma lining in a single plane is uniformly bounded. Like it should be keep moving. So it is actually a counter set. And they proved the following things. First of all, let gamma be a geodesic on a proper K0 space. Then gamma is delta slim if and only if gamma is decontracting, if and only if gamma is n Morse. So basically, these conditions are equivalent. And furthermore, the constants d and n determine each other. So if you know d, then you can determine n. And if you know n, then you can determine d. And they proved that actually the contracting boundary is a quasi-isometric invariant, which is good. So in the proof, this theorem is important, and the direct limit topology is essential. And they were wondering they could use the subspace topology for the contracting boundary, but the answer is no. Last year, Karsian showed that the contracting boundary with the Gromov product topology, subspace topology, is not a quasi-isometric invariant. So we have to use direct limit topology. So now for K0 groups. So we already know that a group G is a K0 if G acts properly co-compactly by isometries on a K0 space X. So the contracting boundary of group is defined by the contracting boundary of the space. Then it is well defined because the contracting boundary is a quasi-isometric invariant, and by Miller lemma. Remark, yesterday we learned this, like the Cayley graph is never K0 if G is not a free group. So we must construct some K0 space X and geometric action on X. So for example, if your group is the free product of G2 and G, then I construct the space R2, the free product of R2 and cross R. Then the contracting boundary of G is homeomorphic to the contracting boundary of X. And some results. So let X be a proper K0 space. Then in general, the contracting boundary is neither compact nor metrizable, sadly. So, and Murray in 2015, he proved that the contracting boundary is compact if and only if it is metrizable, if and only if it is hyperbolic. The contracting boundary can be used to distinguish the difference between quasi-isometric classes of groups, because it is a quasi-isometric invariant. So actually, Sultan and Charney gave an example of two right-angled Coxeter groups, which have the same number of n's, hyperbolicity, relative hyperbolicity, and divergence, whatever, but have non-homeomorphic contracting boundaries. So maybe it can be a tool. Now, more generally, let X be a proper metric space. No condition now. So Cordis defined the Morse boundary. So the Morse boundary is the subset of the Gromov boundary again. But now I consider Morse geodesics, which means just consider a geodesic satisfying this condition. Then it has the following topology. So first of all, the Morse boundary can be viewed as the union of the following sets. And do the similar thing. So for each set, it has the subspace topology of the Gromov boundary, and take the direct limit for the Morse boundary. then his result is that let X be a proper metric space. Then the Morse boundary, the Morse boundary is invariant under quasi-isometry of X, and it is homeomorphic to the Gromov boundary if X is hyperbolic, and it is homeomorphic to the contracting boundary if X is proper case zero. So it is a generalization of the contracting boundary. Remark that contracting property is much stronger than the Morse property. So now groups. So let X be a proper metric space and G be a finitely generated group. Then again, Spark-Miller lemma. Like if G acts on X geometrically, meaning properly discontinuous and co-compactly by isometries, then the orbit map is a quasi-isometry. So the Morse boundary can be defined by the Morse boundary of X. And in this case, the Kelly graph is just proper metric space, and the Morse boundary is a quasi-isometry invariant. So it is homeomorphic to the Morse boundary of the Kelly graph. In 2014, Durham and Taylor introduced a strong notion of quasi-convexity in finitely generated groups, which is called stability. So it is preserved under quasi-isometry. That is a good one. So actually, stable subgroups can be interpreted by the condition on the Morse boundary. So if we understand the Morse boundary better, then we can understand stable subgroups better. And indeed, stable subgroups appear in many literature. For example, if G is a hyperbolic group, then stable subgroups are quasi-convex subgroups. And if G is a mapping class group, then the stable subgroups are just convex co-compact subgroups. And G is a right-angled arcing groups on a finite graph, gamma, then stable subgroups are purely lexicographic subgroups. Those groups are very interesting and many people have studied, so they're very important. And last year, Cordes and Hum defined two new quasi-isometric invariant notions of dimension by using the Morse boundary. So the first one is the stable dimension, and the second one is the Morse capacity dimension. So based on that, I have a lot of questions. So I'd like to understand stable subgroups better, and I'm wondering about some dynamics on the Morse boundary. Also, I'm wondering if I have a homeomorphism between two Morse boundaries, then when it does induce a quasi-isometry, like the opposite way. So I have a lot of questions, but unfortunately, so far, I couldn't get something. But hopefully, I want to get something soon. So it is very new and very interesting subject. So thank you for your attention.